Now let's think about Adleman's experiments. And this is just the beginning of DNA computing. So DNA gives the program. We want to associate with each node a sequence. For example, node 3 could be a sequence. And so it is just the beginning of molecular computing, and we associate for each node, like 4, a sequence, like A, C, T. And of course, we separate it into 2 parts. For example, let's call it gamma, gamma prime, and I will explain it later. And he's the inventor of DNA computing. He was a computer scientist, I guess, and he was reading about biology, and suddenly he noticed that all the things that is happening inside our body is like our Turing machine. So he was working on one of the problems that he solved using DNA computing was Hamiltonian error. This is like exactly like a traveling salesman problem that I've explained on my playlist for approximation algorithm 2 years ago. And Hamiltonian is just another name for traveling salesman problem. We want to visit all the nodes, but we don't want to go more to any states more than once. So this is the graph in Adleman's experiment. For example, the path consisting from going to from 0 to 1 and 1 to 2 and 2 to 3, 3 to 4, 4 to 5, 5 to 6. So this path is Hamiltonian because we have visited all the nodes just once. So the beginning is like this, I explained this. So clearly, if some vertex other than 0 is the input vertex, then the resulting graph has no Hamiltonian path. So we can see that some graphs don't have Hamiltonian path. So let's go and see what is this Adleman's solution, which is based on the following non-deterministic algorithm for solving HPP. First, you have some input in any algorithm. Our input is a graph, for example, a graph of, for example, the nodes of the city. We want to travel all of them. And then among which are designated vertices, because V in, we enter that, and V out, this is the output node. And we generate all possible paths, generate paths randomly in large quantities. We don't care, we just generate all paths, all possible paths that we can go. But I will show you how we use DNA to do all of these things very easily in parallel. We reject all paths that do not begin, for example, it's a sequence, each point is a sequence, and we have different vertices, so a sequence of sequence. And we reject all paths that do not begin with V in and end in V out, because those are not plausible. And we reject all paths that do not involve exactly n vertices. So you have not visited all cities that are in your graph. So what else should we do? So it's like we have a tube of DNA, and then we change this tube, we filter it so that at any step of this filtering experiment, we are getting closer and closer to the final answer by rejecting the non-plausible, non-possible cases. So the idea is that for each node, for example, S2, S3, for each node, you assign a sequence like this. And this has length 20. It means that The first half of that has length 10, and the second half of that has length 10. And we use this function which just maps to its complement. For example, A maps to T, and T maps to A. And so the only function that we are using is just this complement function, which is very popular, and people call it Watson-Crick complement. So for example, complement of C becomes G, the complement of A becomes T, and so on. So it will be referred to Watson-Crick morphism. So S2, which I said that it's just a node in your graph, we do this mapping H, and because this S is a sequence, the mapping of that is a sequence as well. So we have 20, the length of that is 20. And then we decompose each SI into two strands. The reason that we need to do that, because as I said, we have some nodes, for example, SI, Sj, these are nodes of your graph. But if we separate this, for example, if we say Si is Si prime, Si double prime, then you can define your definition of edge is well defined. And for example, this sequence this edge is different from the opposite. So it respects those direction as well, because the way we are define this edge, which is exactly this one, we apply that complementary function, but we pick the second one of the nodes, and we pick the first half of another nodes. For example, if you want to go from Si to Sj, this can be decomposed as Si, and this can be decomposed as Si prime and this can be decomposed as Sj prime Sj. And now we only pick this one and this one. So concatenating them is associated with this edge. The same idea for the reverse edge. So you know how to define an edge using these sequences. So everything is now ready for that algorithm that I showed you, that you at each step you reject some of them, and now you can do that. So quantities considerably smaller than those in Adleman would probably have been sufficient, or a much larger graph could have been processed with the quantities he used. And for example, this edge from node S1 to S3 has this one, which has a sequence. We pick half of this, and then we concatenate. So you know how to create these edges. So when we say we merge, we have two tubes, for example, one tube of DNA strands, which is N1. Another tube is in your laboratory, you have N2. But the union of them, if you combine these two together, you are merging them. Good characteristics of this one, good characteristics of this one, and then you merge it. Amplified, it means that you just make sense for multi-stage. It's just two copy of that. Detect, it means that given a tube N, we return true if N contains at least one DNA strand, otherwise return false. If it is a DNA strand, it's just like that finite state machine, that we had a sequence. If we reach the accept, then we can accept it. Then it is okay. Then it is detected. With the same analogy, we call it detect. For example, in computer science, in theory of computation, we call it accept. We accept a string, which is a sequence of words. And here we use, in biology, we use another term. We call it detect. In computer science, we call it accept. Here we say detect. Because it is one DNA strand, otherwise it is false. We call it, in computer science, we call it rejected. Reject that sequence. Another definition is separate or extract. For example, we want to separate all of those DNA that has a particular W, particular word, particular substring, let's say. And this minus, it means that we don't want to have this particular substring W. For example, this is added. This says that your strand should have A. This one says that your strand should have G. And now detect N. It means that if it is a strand that it is detected, it's okay, it is accepted. Otherwise, it is rejected, it is false. It is not a DNA strand. So the following program extracts from a given test tube all strands containing at least one of the varieties A and G, preserving at the same time the multiplicity of such strands. So your inputs of your algorithm is just this N. This is N is tube, your tube. You amplify it to produce a copy, to have two copies. The first copy, you say that it should have A as well. In the second copy, you say it should have G. And also, you say that this N of G should not contain A. So there is no intersection between them. There is no intersection. So they are not like this. There is no intersection. So it's like here, that A and G are separated. And then we merge them. So here, in this way, we can do lots of computation. There are two important things. Length separate, it means that given a tube N, any integer N, produce the tube, of course, of length less than N, consisting of all strands in your tube N with length less than or equal to N. So we are creating some length. Our basic construction is length. So we say length of, for example, N equal to 5. Another important construction is position separate. So we have a tube of strands N and a word W in your laboratory. We produce, so B stands for beginning, E stands for end. If the beginning of that is W, we call it this one. If the beginning of that is W, if the end of that is W, we call it this. So it's just another construction. And now we're ready to go. Because we have the input, we can filter those strands that have S0 as the beginning, S6 should be the end of that. So it's something like this. Some sequence. The pattern is like this. I like to use the word pattern because it makes sense. S6 is here, and then for the rest of that, you loop over that. We say that this SI should be inside that. And now we detect if it is a DNA strand or not.